Hello, my name is Ivan Trana and I will be presenting you the Ford-Fulkerson algorithm for finding the max flow. First, we need to know some definitions. We will start with flow networks, and as you can see from the example, a flow network is a directed graph in which each edge has a positive capacity, and exactly one node is referred to as a source and one node as the sink. A flow f in the network can be described as a function f that satisfies two conditions. First, for each edge in the network, its flow value has to be between 0 and its capacity. Second, for each vertex in the network, the total flow into that vertex is equal to the total flow out of that vertex. The flow value of the network is defined as the total flow out of the source minus the total flow into the source. Here is an example of a flow network where you can see the flow and capacity values of each edge. Now let's move to our main subject, the max flow problem. The problem refers to finding the maximum flow of the network, or if you want, you can imagine the network as a network of pipes, and we need to find the maximum amount of material that can be pushed from the source to the sink. In order to understand the Ford-Fulkerson algorithm, we need to know some definitions and concepts that it uses. We will start with the residual network. Given a flow network G and a flow F, we can build a residual network GF. To do that, we need to apply the definitions on the slide, but what they are basically saying is that we need to split each edge into two edges, the first retaining the same direction and with a value equal to the subtraction of the flow value from the capacity, and the second in the opposite direction equal to the flow value. An augmenting path is any simple path from the source to the sink in the residual network. The residual capacity is given by the minimum capacity of the edges of the augmenting path. In our example, the residual capacity is equal to the capacity of the third edge, which is 5. If f is a flow in a flow network G and f prime is a flow in the corresponding residual network, then we can define the augmentation of flow f by f prime as the flow of an edge plus the difference of the corresponding two edges from the residual network. Given the previous flow network and its corresponding residual network, we can build the following augmentation example. We can see that the only values that have changed from the original network are the flow values of the edges from the previous example of a simple path. Their values are increased by the residual capacity of that path, namely by 5. Here is an example of a flow network where you can see the flow and capacity values of each edge. In order to fully understand the algorithm, we will go through each iteration step by step, starting with the initial flow network. First, we find a path between the source and the sink. The next step is to determine the residual capacity of the network. We can see that 9 is the smallest capacity along the path, so 9 will be the residual capacity. If f is a flow in a flow network G and f prime is a flow in the corresponding residual network, then we can define the augmentation of flow f by f prime as the flow of an edge plus the difference of the corresponding two. In order to better notice how the algorithm functions, we will work only with the residual network from now on. Now we repeat the process. We choose an augmenting path and find the residual capacity. We augment the path, subtracting each of its edges with the residual capacity, then adding the capacity to the edges in the opposite direction. This way, one of the edges will always be equal to 0, and the algorithm will not be able to form the same path again. We continue on repeating the process, each time choosing a different path, until there are no more augmenting paths. In order to better notice how the algorithm functions, we will work only with the residual network from now on. The running time of the algorithm depends on the order of selecting the augmenting paths. Each iteration takes E time, where E is the number of edges in the network. The flow network increases by at least 1 at each iteration. Therefore, the max flow value must represent the maximum number of iterations possible. Thus, the running time must be O of product of max flow and the number of edges. Let's look at an example to see exactly what I mean by this. If F is a flow in a flow network G and F prime is a flow in the corresponding residual network, in order to understand the Ford-Fulkerson algorithm, we need to know some definitions and concepts that it uses. We will start with the residual network. Given a flow network G and the flow F, we can build a residual network GF. To do that, we need to apply the definitions on the slide, but what they are basically